Hello everyone, I'm V. Sai Sujit of Computer Science Department. Today I'm going to give you a seminar presentation on the thesis Clearing the Skies, a deep network architecture for single image rain removal. Why is rain removal important? So on a rainy day, the images or the videos captured by the outdoor surveillance systems are generally blurred. They contain rain streak. So this will become an obstruction for the surveillance systems to detect the object or recognize the patterns. So hence we have introduced a deep network architecture known as DeRainNet for removing rain streaks from an image. So it's based on the convolutional neural network. We directly learn the mapping relationship between rainy and clean image detail layers from the data. These are some of the results. While the truth is the ground truth and rain represents the rainwater image, and on using a plain CNN, these are the results obtained. We can still see the rain streaks in the plain CNN results, but our results are clean and smooth. Similarly, in this case too, the plain CNN still we can see the rain streaks, but ours is clear and much better. So training. It's extremely difficult to obtain a large number of clean and rainy image pairs from real world data. So what we have done is that we have synthesized rain using the Photoshop. We have created different orientations and intensities. We have randomly collected 350 clean outdoor images from UICD dataset, BSD dataset, and also Google image search. From those clean images, we generated 14 rain images of different streaks, orientation, and intensity for each clean image. So that is 350 into 14. We got 4900 rainy images, each having a corresponding ground truth clean image. So this is the dataset. So this is the original, and other 14 are the synthesized images using Photoshop. So we have slowly increased the intensity and then change the orientation of the rain. Training on high pass detail layer. So we denote the input layer as I and input image as I and clean image output as J. So J is split into J base plus J detail on using a high pass filter. The J detail is the result of the low pass output, and J base is the result of low pass output, and J detail is the result of high pass output. So here we consider a clean image J, and this is a rainy image I, and we have the detail layer J detail as this and I detail as this. We can clearly see the rain streaks in the I detail layer. And using image processing techniques, we also found that the bases of both the rain image and clear image are almost smooth and approximately equal. So this is the clean image, this is the rainy image, and J base is the output of the low pass filter, and I base is the output of the low pass filter. So J base and I base, these are approximately equal because these are approximately equal. As we can see here that J base minus I base is almost empty. So what is our process? First we divide our input image into two layers. One is the detail layer and other one is a base layer. We use a low pass filter for this process, and the detail layer is passed into the convolutional neural network, and we get the output derained detail layer. We enhance the detail layer, and we also enhance the base layer, and we add the detail layer and base layer, and we get the perfect output. So our convolutional neural network has three layers, and these equations represent the convolutional neural network. we use two hidden layers in our DNet architecture. Output. So output is I base plus the result of the convolution network of I detail. But then by using this equation, we obtain the output, but then the outputs are generally hazy. So what we have done is that we have easily embedded image enhancing techniques into our framework to create a better visual results. We use the nonlinear function to enhance the base layer and boosted the detail layer by multiplying it by 2. So our enhanced result equals to I base enhanced plus output of plus twice of the output of the I detail layer. So these are some of the ground truth, and this is the synthesized rain images, and we could see these are the results and these are the other methods which are available. So we could see that our results are much more prominent and cleaner than the other methods. In other methods, the rain streaks are still visible, whereas in our image, our result, it's relatively clean and sharp. So these are more results. Our results are cleaner and sharper than the better methods available. So quantitative measurements. So while the ground truth represents one, and the other one, the rainy image, represents 0.886, our derained results get a score of 0.92 and 0.88. For 100 images, the average was 0.89. And also, according to the quantitative measurement results of BIQI, again on testing with several methods, our methods proved to be better, and the runtime of our method is also very less. For 250 into 250, our method only takes 1.3 seconds, and 500 into 500 image size, our method only takes 2.8 seconds. And for 750 into 750, ours take only 5.4 seconds, where other methods considerably take high amount of time. So this paper was published in CBPR 2017. Thank you.